Welcome to the second part of saponification number. This is the second part of the video, saponification number. In the first part of the video, we have seen what is saponification, what is a soap molecule, what is the origin of the soap molecule, how we can make a soap molecule, and we have also seen the cleansing mechanism and theoretical determination as well as significance. In this part, we will stress upon the practical determination of saponification value. So, saponification number means the milligram of KOH that is required to saponify 1 gram of fat or oil. That is, it is a milligram of KOH that is required to convert 1 gram of oil or fat into soap. Both are correct terms. Now, you can determine saponification number theoretically. That is, there is no need to go for any practical. You can determine it theoretically. But for theoretical determination, you need to know about the oil. Which is the oil? By knowing the oil, what I mean to say is you should know the molecular weight of the oil. Okay? To determine saponification number. You should also know the weight of oil in your hand. Not the molecular weight, the weight of oil in your hand. You should know the molecular weight. For this, you should know the molecular formula of the oil and you should know the weight of oil in your hand. You can calculate it theoretically without doing any experiment. How will you do it? See, for any oil, whatever you take, coconut oil, olive oil, whatever you take, for any oil of any molecular weight. So molecular weight is expressed in grams, correct? 1 mole, you can take molecular formula. From molecular formula you can get molecular weight which is expressed in grams. For any molecular weight of any oil, this is the constant figure. How much milligram of KOH will be consumed? 168,316.8 milligram of KOH will be consumed for any oil of any molecular weight which is expressed in gram. So for such oil, for 1 gram, what will be the milligram of KOH that will be consumed? That will be this divided by the molecular weight. Correct? For 1 gram of such an oil, how much KOH will be consumed? That will be this figure which is constant for any oil divided by the molecular weight of that oil. So you will get for 1 gram how much milligram of KOH is required to saponify it. So that represents the saponification number. So you can get the saponification number in this way. So now suppose the weight of the oil is 5 grams in your hand. So you can multiply it into 5. So you will get the total mg of KOH that is required to saponify 5 gram of that oil. I hope this one is clear. This is the theoretical determination of saponification number. Now you have to determine it practically. Okay, when will we go for practical determination? That is a question that comes in our mind. If you don't know anything about the oil, you don't know what the oil is, you don't know the molecular weight of that oil, okay, you don't know anything about that oil, only you know the weight of the oil. In such case, you can go for its practical determination. How will you do it? Let us look into it. For that, you have to take a round bottom flask like this. Excuse me for the diagram. So you have to take a round bottom flask. You take that oil sample and put it inside it. But before putting it inside, don't forget to take the weight of the oil sample, because saponification number at last we have to express per gram of oil. So don't forget to take the total weight of the oil that you have taken. Okay. Now the oil is in the round bottom flask. Now dissolve it in a suitable fat solvent. Okay, so there are a lot of fat solvents. Here we are using ether ethanol mixture as fat solvent. Okay, these are volatile. Okay, that is why we have taken round bottom flask, so that we can close it. Okay, we can warm it using reflex. So that is why we have taken round bottom flask. So just dissolve it in this fat solvent. Fine. Now what you do in the second step, you add 0.5 normal KOH. Okay, so for that you pipette out 0.5 normal KOH. So you take 25 ml. Take excess amount of 0.5 normal KOH. So you can take out 25 ml and you can put in the second step 0.5 normal KOH excess. Okay, excess. Now what will happen? What will happen? Yes, saponification will take place. So what will be the reaction? Here there will be a triglyceride molecule, right? And that would react. This is the triglyceride molecule, right? And it would react with KOH, which is ethanolic KOH. And what it would yield? It would yield the component alcohol, which is glycerol, and it will also yield the corresponding potassium salt of fatty acid. Potassium salt of fatty acid, this is nothing but soap. So when you add 0.5 normal KOH, excessive amount of it, some amount of KOH will react with triglyceride molecule, and it will convert the triglyceride molecule, whatever it is, how much weight it is, however the weight it is, it will convert that amount into soap. So you have subjected it to saponification by alkaline hydrolysis. Now I have used the word hydrolysis. Hydrolysis actually means addition of water. Where is water in this? For that, kindly refer to my first part of the video where I have explained how water comes out of ethanolic KOH. Do refer the first part of the video. Now in this part of the video, we don't need to bother about that. We just need to understand that some amount of KOH has reacted with the triglyceride molecule. So that means there is a remaining KOH in the system. So what will you do with the remaining KOH? What will you do with the remaining KOH? What is it, KOH? It is a strong what? Strong base. So you can go for acid-base titration against a strong acid. So take a burette, okay, and go for, this is, take a burette, go for titration against 0.5 normal HCl. But before going for titration, don't start the titration now. Before going for titration, in the third step, add phenolphthalein 1 ml. So when you add phenolphthalein 1 ml, what would happen here? It is having excessive KOH. The solution here is basic solution or alkaline solution. In alkaline solution, phenolphthalein, it would exist as ionized, in an ionized manner. The phenolphthalein, it would lose H plus and it would exist in ionized manner. In ionized manner, phenolphthalein is pink in color, or correct? In ionized manner, phenolphthalein is pink in color. So the solution inside this becomes pink color when you add phenolphthalein. Okay, so that is what you do in the third step. So after you add phenolphthalein, immediately a pink color will come because the solution inside is alkaline, and phenolphthalein would exist in ionic form in alkaline medium, and that ionized form of phenolphthalein is pink in color, and therefore the solution becomes pale pink in color. So now inside it is pink in color, pale pink in color. Now you conduct the titration. You are titrating, actually you are titrating excessive amount, unreacted amount of KOH, correct, against HCl. What would happen? As each drop falls, what would happen? That HCl would react with KOH, and that would result in what? a salt plus water. So this reaction will go on. As each drop of HCl falls into the RBF flask, each drop of HCl would react with each drop of KOH and it will produce potassium chloride and water. So slowly the solution inside is turning out, is proceeding to becoming neutral. Slowly, drop by drop, this alkaline solution is becoming neutral. When the last drop of HCl reacts with the last drop of KOH, the solution here becomes perfectly neutral. That is, pH becomes 7. We don't know when the pH becomes 7. We don't know. When a drop in excess of HCl falls, what would happen? So when one drop in excess of HCl falls, there will be no KOH in the system, right? So there is nothing to react with. So when it falls, the solution here becomes acidic. What it would become? Acidic. In acidic pH, phenolphthalein ionized, it will accept H plus and it will become phenolphthalein unionized. Phenolphthalein ionized is pink in color, and when its solution becomes acidic, it receives H plus and it becomes phenolphthalein. The unionized phenolphthalein is colorless. It is colorless. So the change in color is from pink to colorless. It is pink to colorless. So now when the excessive drop of HCl falls, when an excessive drop of 0.5 normal HCl forms, there is no KOH to react it with. There was initially 0.5 normal KOH, excessive. But now there is no KOH to react. So that excessive drop makes the solution inside acidic. When it becomes acidic, the phenolphthalein, it accepts the proton and it becomes unionized phenolphthalein. The unionized phenolphthalein is actually colorless. So the solution which was initially pink suddenly becomes colorless by addition of excessive drop of 0.5 normal HCl. So when it becomes colorless, that is the time you realize that all our KOH in the round bottom flask is consumed. Consumed by whom? Consumed by HCl. And there is no KOH that it could react with. That is the time you need to stop the titration. Stop it. Stop the titration. Note down the titer value. This titer value I will call as sample value, because it was taken, this titer value was taken when the sample of oil was present. So I will call it as sample value. Correct? Now in the next step, you conduct blank. You conduct a blank titration. So blank titration, you do the same thing with blank titration. But this time don't add sample. Okay, no oil is there. That means you have to add solvent, ether, ethanol mixture you add excessive amount of 0.5 normal KOH, that is 25 ml, and then in the third step you add phenolphthalein. Then you go for titration against 0.5 normal HCl. Same thing will happen. The first reaction won't happen. The reaction with triglyceride will not happen. Reaction between HCl and KOH would happen, and whatever KOH we have used, that is 25 ml, that much KOH is available for reacting with HCl. So the blank value will be more than the sample value, because in sample value only some amount of KOH, the remaining amount of KOH was titrated against HCl, but in blank the whole amount of KOH has been titrated against HCl. So the blank value will be more, right? So now you can calculate titer value. Titer value true titer value or titer value is equal to blank value minus sample value. What is the blank value? What is the blank value? The value when total unreacted. The value of total unreacted KOH. Correct? That is 25 ml. That is blank value. And what is sample value? Unreacted KOH when oil was present. Correct? When oil was present. So when you are subtracting these two, what will you get? Blank value is total unreacted KOH, that is value because of total unreacted KOH, and sample value is the value because of unreacted KOH when oil was present. If you subtract it, what you will get? You will get reacted KOH value, right? I hope you have understood this concept. Blank value is the value when no KOH reacted with triglyceride, that is for total unreacted KOH, 25 ml KOH, and sample value is the titer value for unreacted KOH when oil was present. When you subtract that, you will get the value for reacted KOH. So here we assume that the bound KOH has actually reacted with HCl. Actually it has not reacted, but here we are assuming that the bound KOH has reacted with HCl. Okay, so that is how we get the reacted KOH value. So that is, I will call it as the true titer value. Fine. Now you need to understand, you need to know the equivalency weight factor. Okay, so let us see what is equivalency weight factor. Now for 1 ml for 1000 ml of one normal HCl, it is equal to 1000 ml of one normal KOH. That is, if 1000 ml of one normal HCl is used, it can consume 1000 ml of one normal KOH. That is equal to 56.1056 gram of your KOH. That means if 1000 ml of one normal HCl comes from the burette, it can consume 56.1056 gram of KOH in the round bottom flask. Okay, so now I will half it. Okay, I will reduce it. That means 4000 we are used 0.5 normal HCl and 0.5 normal KOH. So we have to divide it by 2. For 1000 ml 0.5 normal HCl is equal to 1000 ml of 0.5 normal KOH. Am I right? Just half it. That is equal to 28.05 gram of KOH. Because we have used 0.5 normal in our experiment. So this is the equivalency factor. You just half that because we have used this much. Why we have used 0.5 normal? It is because we should get a burette reading. Okay, one normal HCl is a very big strength. So we will not get a sufficient burette reading. Maybe we will get 0.1 ml or 0.2 ml. That would be difficult to analyze. So we need a lesser strength HCl so that we get a sufficient reading. Okay, a notable reading. Because maybe that oil may be less in our in our round bottom flask. So we need sufficient dilution so that we get a sufficient reading. That is why we have used 0.5 normal HCl in our burette. Okay, so that is equal to 28.05 gram KOH. Now we need to know for 1 ml, correct? Because 1000 ml no one will use in burette. We need to know for 1 ml. So 1 ml of 0.5 normal HCl it equal to 28.05 divided by 1000 gram of KOH. So that will be divided 0.02805 gram of KOH. Correct? Now this, the definition is milligrams of KOH required. Correct? So you convert this into milligram. How will you convert it into milligram? By multiplying it into 1000. If you convert it into milligram, what you will get? 28.05 milligram of KOH. That is 1 ml of 0.5 normal HCl, it is equivalent to 28.05 milligram of KOH. So that is the relation between the burette, the titrant and the KOH in the round bottom flask. If 1 ml is consumed from the burette, it means there is 28.05 mg of KOH in our round bottom flask. Okay, so now we have come to know the equivalency weight factor also. Now let us look at calculation. So this is the sample value, saponification value. Let us look at how we calculate. True titer value or titer value into actual normality into 28.05 milligram, of course, divided by total weight into given normality or expected normality. So I will tell you how this part came. See what I told you initially, that 1 ml of 0.5 normal HCl is equal to 28.05 mg of KOH. Didn't I tell you that? So for 1 ml of 1 normal HCl, how much mg will be consumed? Yes, 28.05 divided by 0.5 mg of KOH. Now if today in my experiment my normality is not 0.5, it is 0.4. If it is 0.4, then for 1 ml of 0.4 normal, what I will get? 28.05. This is into 1, okay, divided by 0.5 into 0.4. So that is how it is coming. Actual normality is 0.4, expected normality is 0.5 and 28.05. So that is how it is coming. When you divide actual normality by expected normality, you will get the true normality of the titrant, right? When you multiply the true normality of the titrant with what is the capability, okay, what is the capability? This is the capability of the titrant, right? 1 ml is capable of neutralizing 28.05 mg of KOH. So if you are multiplying the true normality of the titrant with the capability, correct, you will get for 1 ml of original normality, right? So you will get the capability of 1 ml of original normality. If you do multiply it by true titer value, by titer value, what you will get? You will get the total amount of KOH, right? That is there in the round bottom flask. If you divide it by total weight, you will get for 1 gram of oil, right? I hope you have understood this concept. Okay, so here I have made it known. This is the equivalency weight factor. Now our normality is not 0.5, it is 0.4. If it is 0.4, then for that amount of strength, if 1 ml is consumed, then this much mg of KOH may be in the round bottom flask, right? So that is for 1 ml. Today, suppose 5 ml was consumed, correct? So in that case, you have to multiply it by 5, correct? So if you multiply it by 5, you will get what? Total amount of KOH that is available in the round bottom flask, right? But saponification number you have to express it in per gram of oil. So just divided by total weight of the oil, you will get the saponification value. Dear students, I hope you have understood the class. For understanding the significance of saponification value, do refer to the first part of the video. Dear students, hope you have understood the class and hope you have liked it. If you have so, please do not forget to subscribe the channel and to like and share it. Thank you very much.